Thank you, Stefan. Thank you for the introduction. Hi, everyone. My name is Rohit, and I am part of the HPC and AI software architecture team in NVIDIA's networking organization. And I'm going to present this paper, DOCA UROM, on behalf of the seven team members who wrote this paper. So it's a collaborative effort between the research team that's the architecture team that I'm part of, and also the product teams that helped bring the our POC into what is now called Doka Euro. Okay.
You just have to click, I think, somewhere. And try again.
Oh, okay. All right. So we have had a pretty good setup in the morning in the previous talks uh, about DPUs and how they are so important, how they're emerging computing technologies. So which leads us to look at how modern systems look like. So we can see that the modern server has CPU, GPU, and also now DPU components. We are somewhat fairly familiar with the CPU and GPU parts of these modern servers. But the DPU part is emerging, and it's one of the reasons why this workshop exists, right? It's a fairly evolving landscape, both from a hardware and software perspective. And if you zoom into like what exactly the DPU is, over here I have a abstract representation of the DPU's architecture. Typically, it's a system on a chip, and they are indeed part of the networking infrastructure. But if you look at the different components on the SoC, we can see it's a pretty rich resource. And what do I mean by that? So we can see that we have a compute subsystem. So we have multiple cores. And it's not just the NVIDIA Bluefield DPUs that have this kind of general purpose CPUs on the DPUs. We also have Intel IPUs. We also have AMD's Pensanto DPUs. They offer this general purpose CPUs as their weight of compute on the DPU. In addition to that, we also have accelerator engines. So things like a DMA engine that you can program to exchange data between the DPU and the CPU memories, and also sometimes the GPU memory as well. And of course, we have the bread and butter of the DPU SoC, which is the networking subsystem, which is the heart of the evolution of the DPU, right? Like this contains all of the smart NIC programmable pipelines and also the networking interface card itself. So let's see. Okay, so the DPU is a very rich resource, and we want to be able to utilize them to accelerate our workloads. And so, what are some ideas? I think we've already covered some ideas in the few talks here. The first and foremost, very easy to understand, kind of like an obvious use case is communication progress. You want to have you can use the cores on the DPU to progress your communication schedules, and that's a pretty straightforward use case of the DPU's capabilities. We also could define new communication primitives like RDMOs or remote direct memory operations. So yeah, I'll talk a bit more about this later in the presentation, but the idea over here is to add in some level of compute to your RDMA operations that have already existed, so that you can execute more complex operations like indirect puts and indirect gets. So that way you can reduce round trip latencies or multiple round trip latencies and just have one by utilizing the compute capabilities on the target. And we can also notice that we have a significant amount of memory on the DPUs. And so that leads to the idea of maybe you can expand the memory on your system by utilizing the memory that's available on these DPUs. So, all that to say that there's many ideas that we can explore on utilizing the DPU's resources. And so our goal over here for all of these ideas is that we want to offload them to the DPU and utilize the resources. But I think for any idea that requires an exploration of DPU's capabilities, the first question that people run into is how do we efficiently offload, right? I think this is the main concern of using DPUs. We have a lot of ideas. The problem is that when it comes to offloading them, it's not very straightforward to do that, and that is kind of a big bottleneck in terms of exploring the use cases of DPUs. Uh, what makes it harder is that different use cases have different needs from an offloading framework, and we'd also not rather create use case specific offloading frameworks. So what the community kind of needs is a versatile and efficient DPU offloading framework. And by versatile, I mean a framework that applies to many use cases, not just one or two. And efficient meaning that the offloading itself has to happen in a productive manner, so that if you offload your idea, you don't want to incur the overheads of poor offloading, where you would lose out the benefits of the offloading idea itself. So there are various challenges in creating an offloading framework. The first and foremost is the deployment of these offload execution units on the DPU itself. And you obviously want to have efficient communication between the DPU and the host. And you also want to have coordination between the applications process groups, like we have in MPI or PyTorch or any distributed programming model, and the process groups that you have on the DPU. Because each of these different processes that you have on the CPU, they would create their own independent workers on the DPU. Okay, so we've identified a gap in the community for a versatile and efficient DPU offloading framework, and that's where we want to bring in DOCA UROM. So with DOCA UROM, we want to fill this gap. And the goal over here is that as runtime developers, we want to focus on the how of offloading. So we develop this framework that focuses on efficient offloading, so that the users of DOCA UROM, who would be domain scientists or offload idea explorers, they can focus more on what to offload rather than how to offload. And we present DOCA UROM as this versatile and efficient DPU offloading framework. What we have identified over here are abstractions that apply to a variety of use cases. And it's primarily based on a client-server model, but it's also very applicable to the process group models that we see in traditional HPC use cases, and also the modern distributed AI training use cases. And the key part over here is that the users of DOCA UROM can use this framework to develop their own offloading logic. So all they would need to do is plug in their offloading logic through what we call plugins, and use the rest of the framework to perform the management of the DPU's resources. So I'll be going over the details of DOCA UROM's architecture. But I did want to say that this project kind of started off as a research project to identify what exactly is needed for an efficient offloading framework, and now it's deployed for NVIDIA DPUs through the DOCA SDK. So it's already available on the DOCA platform, so if you have the DOCA platform, you should be able to use it. It also has like user guides on the website, and also sample codes in the SDK itself. Okay, so I know we talked about a different, I talked about a few ideas previously. And this slide over here is basically to capture what families of ideas that we are trying to target with this offloading framework. And so we categorize the sets of ideas into three execution models. So first is data parallelism. So here, the idea over here is that you use the DPU cores directly to perform your applications compute, like we saw earlier in some of the talks as well. So this falls under a direct use case of the DPU, where the application is directly using the resources of the DPU. The second one is task parallelism, where you have you are performing different types of tasks between the host compute elements and the DPU's compute elements, and then you're coordinating them in a event-based fashion. And this is also another way to directly use the DPU from a host perspective. And finally, there's a third model called library offloads, where the usage of the DPU is kind of abstracted by by a library, by a middleware layer. So things like UCC, for example, or MPI, they could transparently use the DPU for progressing their communication primitives, and that way the application user is not really interacting directly with the DPU, but indirectly through the use of runtimes. And all of them rely on the same key functionalities, all of the three models. I mean, these functionalities include management of the process on DPU and also efficient communication of between the host and the DPU. And so for our work over here, we focus mainly on the library offloads programming model, but the architecture should also apply to the other execution models as well. Okay, so let me get into the architectural components of DOCA UROM. Here is an overview. We have mainly four components. We have the UROM service. We have the UROM worker and plugins, which is like which are mainly the components where the logic executes for the offload. We have the UROM communication channel, which is responsible for the communication between the host and the DPU. And we have UROM domains, which is a way to abstract out process groups on the DPU itself. The figure over here is kind of showing a high-level view of how we can how a deployment looks like with UROM. So you can see that on the host we have multiple app processing elements. These can be MPI ranks, OpenSHMEM PEs, or PyTorch ranks. And so these are all UROM clients. So they are users of DOCA UROM. And each DPU hosts a UROM service. And the UROM service is basically taking care of managing the resources on the DPU. And we have a bunch of workers running on the DPU, and they're running different plugins. So they could be running the same plugin or different plugins, as you can see in this picture over here. Now, if I'll go into each of the different components in more detail. So the first one is UROM service. So UROM service is basically a daemon that's running on each DPU. It's a way for the users, the UROM clients, to discover whether or not there's any UROM services available on the DPU. It is assumed to be running on the DPU before the app is running itself. And the main responsibility over here is that it's managing the UROM workers. It's creating them. It's destroying them based on the commands that it gets from the hosts. And it's present on the DPU to ensure secure coordination with the application, to ensure that only authenticated users are able to manage resources on the DPU via the UROM service. UROM plugins and workers. So plugins are basically the offloading logic that runs on the DPU. So for any logic that you would have, or any service that you would provide on the DPU, you would deploy it as part of a UROM plugin. So if any developer or any user of DOCA UROM wants to test out a new idea, you would define a new UROM plugin, and that's your means to deploying the logic on the DPU. UROM workers are basically offloading execution units that are running the plugin's logic. Okay, so execution units could be like they could be the processes, or they could be threads, and each worker has a unique ID within a DPU. So yeah, so every execution unit is addressable. And clients can then connect to either one or many workers. Just really depends on how the clients decide to deploy the workers on the DPU. And one worker can also then be connected to one or more clients. So this allows flexible mapping between the client processes and the workers on the DPU. And in addition to there being a unique ID on a local DPU domain, we also have the idea of a unique global ID for in a distributed process. So you can have a unique ID to identify your worker that across multiple DPUs. And it's coming as part of the UROM domain concept, which I'll go over soon. All right, so and we have the UROM communication channel component. So this one is it's not really visible to the end user, but it's used by the DOCA UROM runtime system for any communication that happens between UROM clients and the service that and the workers that run on the DPU. So the abstraction over here is a simple push and pop interface. And what happens over here is that we have commands going from so we call them commands for messages that go from the host to the DPU, and for messages that go from the DPU back to the host, we call them notifications. So UROM clients, they push commands and they pop notifications. Similarly, UROM services and UROM workers, they will push notifications and they will pop commands. And one interesting thing about this communication channel component is that it has multiple backends. And the reason for this is that we want to explore the continuously evolving landscape of different host DPU interfaces, and we want to ensure that the performance is that we are able to deliver the best performance as and when new technologies come out and explore them as and when they come out. Okay. Finally, we do have UROM domain and active sets. So a UROM domain basically is a concept that identifies a group of UROM workers. Okay, here we go. So workers in a domain can communicate with each other. So like MPI-COM world or OpenSHMEM team world, there is a UROM domain world. And within this world, you can uniquely identify each worker. And this means that all the workers that are part of a UROM domain can talk to each other, and all the connections are established, like we have it in MPI-COM world or OpenSHMEM team world. So the domain creation actually is a bit of an expensive operation, and it relies on an all-gather operation that is performed by the clients on behalf of the DPU workers. The all-gather is responsible for exchanging the addresses to connect the workers to each other. The domain creation is a expensive operation. And so if you want to create multiple groups after you have a domain world, we have the concept of active sets, which is very similar to the OpenSHMEM's active sets in the sense that they're also groups of workers, but they're a map onto this domain world. So you don't have to incur the cost of exchanging addresses again every time you want to create a new active set. You just build on top of the domain world that you have created before. And this is so the UROM domain concept is important over here because HPC programming models and also AI frameworks like PyTorch, they're all based on groups of processes, and UROM being fundamentally a client-server model needs to have this domain concept in order to be able to support the higher level programming models in an efficient manner. Okay, so for the rest of the talk, I'll focus on the use cases with DOCA UROM. And the primary goal for showing the different use cases over here is to show how DOCA UROM maps to the different types of use cases. And for each use case, I'll talk about what we did in DOCA UROM and also some performance evaluation as well. Okay, so the first one is like I talked about before, and also has been talked about in this workshop, is actually progressing your communication in the network. So we evaluate the progress of non-blocking collectives, and the problem over here is that non-blocking collectives are typically not progressed until they're checked for completion. and this is very common in scientific and AI application. So this use case was primarily explored by Farrell from our team, who is also very actively developing and supporting a UCC. So for this particular work, we develop a DOCA UROM plugin, actually a DOCA UROM UCC plugin that is also available on UCC's GitHub repository, ready to use with DOCA UROM. And so what happens over here is that each process of an application creates a UROM worker that runs the DOCA UROM UCC plugin. The application then establishes the UROM domain world, which connects all the UROM workers like I talked about. And the application also sets up a data channel with the corresponding UROM worker using a cross-Gavami memory key or the alias memory key, like Rich talked about in his presentation on Bluefields. So this allows the UROM worker to issue networking operations that access the memory regions that are registered on the host. And like I said before, all of this is encapsulated inside the UCC library. And so all the users of UCC libraries can just utilize this offload transparently. And so for our evaluation, we use the OSU microbenchmark, the all-to-all microbenchmark, and we added in some overlapping computation into that benchmark. And we toggled the offloading of the collective progress. And what we can see from the graph over here is that with the offloaded progress, we can achieve nearly 100% overlap with the computation, which is not possible without the offloading. Okay, so that's the first use case. The second use case is what I also briefly talked about earlier, is the remote direct memory operation. So this is a new communication primitive that adds in a compute element towards the RDMA communication primitive. This is not a new concept, and it has been explored in the past. But like I said, it enables efficient implementations of some complex communication operations like indirect puts and gets, which typically require multiple RDMA round trips. Zach from our team has primarily driven this work or has explored this idea. So in the context of our DMO, we have three components. We have a initiator, we have a target, and we have a server. And so we define an RDMO plugin and define the new commands for this plugin. So what applications do over here is that they use the RDMO plugin API to query the address of the local server and exchange that with the other clients to establish the necessary connections. And that's what the application has to do on the DOCA UROM side of things. Now, to evaluate the efficiency of this RDMO plugin, we define an operation called append, as I've shown in the top diagram over there. So if you look on the left-hand side, if you want to do an append with RDMA, you would need to do first a fetch and add to a pointer, and then an RDMA put to the fetched address. But if with an RDMO operation, an append operation, what you could do is you would incur only one round trip latency as opposed to two, because the DPU on the remote side will take care of appending to the right location. So from the graph here, you can see that we have a pretty high benefit of using RDMOs over RDMA operations with DOCA UROM. Okay, and the last use case that I kind of want to go over was the idea of memory expansion. We explored this in the context of AI model states. I primarily explored this myself, this use case. And the problem over here is that, AI workloads, they have really high memory requirements, especially for configurations that deliver high performance. So you can think of like large batch sizes, or higher interleaving pipelining factors. All of these that give high performance in training typically require higher memory as well. With that, so what happens with the limited resources we have on the CPU and the GPU, sometimes enabling these high performance configurations can lead to out of memory issues, even though compute is capable of handling those high performance configurations. So, DPUs do offer a second tier memory space that can help with the memory size requirements, and also can help with the potential bandwidth contentions. Because when you don't do any sort of offloading, you have your compute bandwidth that is also contending with your communication bandwidth. But with DPUs, you have an isolated memory system, and with offloading, you can separate out the usage of the DPU's memory system for communication from the GPU's communication memory system for computation. So what we did over here with DOCA UROM is that we developed a object manager plugin to send and receive objects or to offload objects from the DPU's memory space along with some communication operations on it. And what we did is that the top graph over here kind of shows how if you were to offload a 500 billion parameter model using DPUs, the top graph shows the scales at which you can actually enable your model training. So if you look at just the H100s without offloading, we can see that we would actually need more than 2K GPUs to just even run the model or to train the model. But if you use Bluefield 3s, which have around 16 gigabytes of memory, yeah, or I think in this case it's 32. We can actually start fitting the model with just 512 GPUs. And so that means you can at least start training a model with 512 GPUs. For the implications on performance, we ended up developing a mini app that mimics the forward pass of AI training. So what we did was we had a nickel all-gather that is overlapping with a memory-bound computation kernel. And this kind of mimics the forward pass in at least the FSTP style training. And so what we can see with the graphs over here is that even with offloading, we don't really have an impact on both the communication bandwidth or the computational bandwidth. So, and that's the best case we can achieve over here. So what this means, what the two graphs over here mean is that you can use offloading to train larger models without hurting performance. And so these are the kind of ideas over here that DOCA UROM as a framework allows us to explore now that we have this framework. And I think I'll conclude over here by saying that DPUs they are part of the networking infrastructure, but as we have seen, they're more than just networking endpoints. They're a pretty rich resource, and the resources can come to good use. What we lack as a community is an efficient and flexible framework that enables the exploration of these DPU-based offloads. And DOCA UROM in this paper, we present this offloading framework as a solution to address these challenges. So with that, happy to take any questions you may have.
Thanks, Rohit, for the talk. Any questions from the audience?
Thank you for your talk. So when we are looking at HPC clusters or in AI clusters, usually you don't see the DPUs. Mainly, you will see the connectics, usually with InfiniBand, or you will find NVLink on the AI clusters that are main one with InfiniBand. How do you see the implementation of such great work? This is great work, but the big question is how can it be adopted if eventually the vendors or the customers are not purchasing the Bluefields into the environment? So
yeah, I think that it basically boils down to a chicken and egg problem, right? Because customers want to see values of DPUs to be able to purchase it, but to see the value, we kind of have to develop the software framework. So we're kind of in this like transitionary phase where someone has to take the step first, and it's easier as software developers to take the step first to develop the infrastructure so that we can showcase value going forward, right? And I agree that the bigger AI hyperscalers, they don't have DPUs at least on the East-West fabric. They have it on the North-South fabric, yes. But there are these smaller clusters that are kind of like test beds for research, which do have DPUs. And for those, and I feel like having a good framework for those systems at least can help showcase values for DPUs for these larger scale clusters. There will still be gaps in evaluation, I agree. But things are always changing. And so we hope that with the efficient offloading framework, we should be able to get better at showing the value of DPUs.
Other questions? Well, then I have one.
Go.
One of your motivations at the beginning was like having kind of a portable model. You mentioned like different vendors coming up with like DPU-like devices.
Yes.
And like, how portable is your approach that you just presented?
Yeah, that's a good question, and a question that comes up a lot. That definitely came up a lot in the reviews as well. The answer to that is, yeah, DOCA UROM is going to be meant to be run on NVIDIA DPUs only. And one of the motivations to get this in a workshop format was to share the architectural components of DOCA UROM. And the goal over here is to be transparent on what kind of components are present in DOCA UROM so that vendors of other DPU offerings can learn from our findings and develop a similar infrastructure for their offerings. Yeah, I hope that answers your question.
Okay, we have another question. Quick one, please.
It's actually strongly related to this question. So I know it's not gonna happen because, of course, media would not like to, But anyway, it's just like, what do you think? Would it be possible, even though now it's tightly bound to DOCA, which is a customer product, but what you're proposing, like to provide a general API that then each vendor can, I mean, like to the user expose your work as a general API, and then it doesn't matter which hardware you are running on. The user just has the API in order, which allows it to program the DPUs, and then it gets matched to Bluefield or Huawei DPUs, whatever hardware you have in the backend. Like conceptually, do you think can it be generalized?
Yeah, I think from a conceptual perspective, yes, it can be generalized, and honestly, that was the motivation when the project first started. That it was not meant to be tied to NVIDIA DPUs only. Of course, NVIDIA has its own interests, and at the same time, I think the architectural components can be generalized. But I think the key idea over here is that the abstract layers or the open source layers like UCC or middlewares, they can be the abstraction that users interface with, at least for cases where library offloads can be enabled, right? So you can imagine the UCC layer being able to support AMD DPUs, NVIDIA DPUs, and Intel DPUs through the vendor-specific offerings. And so the users don't have to rely on that or rely on development for each different vendor. It's the runtime that kind of takes care of that. But yes, it would apply only in the case for library offload related execution models.
All right, then thanks, Rohit, again. Thank you very much.
Yeah. Thanks, everyone.